Analytical reconstruction methods are based on the Fourier slice theorem. So in this video, I'll explain exactly the concept behind this theorem and how in theory it can be used to build the reconstruction from a projection data. In another video, I'll then also prove why the Fourier slice theorem is the way that it is. Now, as its name implies, to fully understand the Fourier slice theorem, you do require at least some basic knowledge on Fourier analytics. So if you're interested in learning more about that, look in the description below this video to find some links that will help you with that. Anyway, so we have a two-dimensional object function f represented on a Cartesian domain. Now, to represent this function on the Fourier domain, you can simply apply a two-dimensional Fourier transform on it. But of course, in tomography we don't know the object function. What we do know, however, are its detector functions for a set of different angles. Now, the Fourier slice theorem states that a one-dimensional Fourier transform of the detector function at an angle theta is in fact exactly the same as a line through the two-dimensional Fourier representation of the entire object. Even more, it is the line through the origin at the exact angle theta. So by measuring a single projection of an object, we are able to fill in a single line in the Fourier domain. Obviously, as we then acquire projections from multiple angles, we can then essentially construct the full Fourier representation of that object. And once the Fourier domain is fully built, a two-dimensional inverse Fourier transform can be applied on that data to retrieve or to reconstruct the original object function. Now, sadly, there are one or two problems with this approach, all coming back to the fact that the amount of measurements in practice is finite, which leads to a Fourier domain that is sampled in a difficult to work with way. One thing you'll note immediately is that the Fourier samples lie in circles rather than on a square grid, which is required for practical algorithms that perform the inverse transformation, such as the fast Fourier transform. This means that we'll have to apply interpolation in the Fourier domain, which is not necessarily something that we like to do. Also note that the sampling distribution of the Fourier domain is much denser near the origin than it is for the outer regions. This means that for the lowest frequencies, there is lots of data available, meaning that these low frequencies will be reconstructed fairly accurately. The high frequencies, however, which is where most of the finer details of the object are located, are not that greatly sampled and will not be accurately reconstructed after the inverse Fourier transform. And this will lead to very blurry images. Now, does this mean that the Fourier slice theorem is useless in practice? Not really, because even though you can't use it to directly create reconstructions, it does form the basics for another reconstruction method called filtered back projection. And filtered back projection cleverly manages to overcome the problems of the Fourier slice theorem by introducing an additional filtering phase and by replacing the inverse Fourier transform with a different operation. But more on that in a future video.